In this slide, we are going to cover the topic upthrust in a fluid. Now, first of all, from where the concept of upthrust comes. Upthrust is basically, we should say that upthrust, upthrust is basically is a force experienced. Upthrust is a force experienced by an object. Upthrust is a force experienced by an object immersed in a fluid Upthrust is a force experienced by an object immersed in a fluid due to the pressure difference between the top pressure difference between the top and the bottom of the object. Now, assuming that you know all the formulae from your O level, you know that generally for pressure in liquids, we use the formula P is equal to rho GH. Actually, this is pressure difference, yet you can call it pressure. So, formula for pressure that we used in fluids generally, you can say typically in liquids, is rho GH. If we explain this formula, it is P is equal to rho into G into H. P is the pressure due to liquid generally. We will understand the concept for liquid, yet later on we'll also apply that to the gases. Rho is the density of liquid, G is the acceleration due to gravity, and H is not the height but the depth. For example, when you apply this formula, you have to be careful about one thing. That one thing is, for example, if this is the surface of the liquid, then if this is the surface of the liquid and you find pressure at a point, for example, this is a point P here, then one important thing is that, for example, the depth is H1. We take depth from the surface. And height is taken from the bottom. This H2 is height. Now, students generally mix these two things. I should clear that when you calculate pressure on P, pressure on point P is equal to, it should be rho G H1. If someone writes it rho G H2, then it is wrong. So it is rho G H1. You have to use the depth, not the height. So pressure depends on the depth. Now let's assume for a liquid of uniform density throughout the liquid. If a liquid has uniform density, then we can say that since P is equal to rho into G into H, here you see that these two will be the constant as Rho is constant, it's a uniform density, and G is acceleration due to gravity. For small depths or heights, it is taken to be constant. So pressure in a liquid is depth dependent. So pressure in a liquid is depth dependent. If we just want to understand the concept, then we need to understand that if you take a liquid, then on the surface of the liquid, what you will get is the atmospheric pressure due to atmosphere. Here you have purely atmospheric pressure. Now let's suppose this is the surface of the liquid, and you're moving downwards. This depth is h1. You are here. This depth is h2. You are here. This depth is h3. All the points on this line, they will experience a total pressure of P atmospheric Okay, students, if we write different values of pressure, then P total here is P atmospheric plus rho G H1. Here it would be, you can write P total is equal to P atmospheric plus rho G H1. Sorry, rho G H2. And here it would be P total will be equal to P atmospheric plus rho GH3. So these are the values of pressure at this point, at this point, and at this point. However, at the surface of the liquid, all the pressure is due to the atmosphere, and it would be P atmosphere only, as no liquid is involved. Now, if we only look for liquid pressure, the terms rho GH represent the liquid pressure. We have to add liquid pressure to the atmospheric pressure to get the total pressure. And as we are moving towards the depth, the liquid pressure is increasing. For example, if we want to represent the liquid pressure only, then we must know that the first important thing is liquid pressure acts inwards from all sides on an object. And there are some important factors that you must know, which are, why is pressure a scalar? Because when you look for pressure, pressure will not follow vector addition. And interestingly, pressure will not even follow the scalar addition. I should clear that. For example, you have this box. On this box, for example, this is a box in a liquid. a box in a liquid. I will try to explain the concept of pressure using the example of this box. For example, the box has dimensions. Let's go with 10 meter each side. This side is 10 meter. This side is 10 meter. This side is 10 meter, and this side is 10 meter as well. Now, if the total force on the top is, let's suppose, 100 Newton, and total force on the bottom is, let's suppose, since bottom is at more depth, so the force on the bottom could be, for example, 200 Newton. Here, the density of the liquid is not given, so we can go with any forces. We have to understand the concept. Now, for example, the force on the side, on this side is, for example, 150 Newton. And the force on the other side is, for example, 150 Newton. Now, when you calculate pressure, this is phase X, this is Y, and this is Z. Pressure on phase X would be 100 over, the area would be 100 meters square, and it is 1 Pascal, for example. If you calculate the pressure on the bottom face, or the, like you say, that face is, you can call that as bottom face, then it would be 200 Newton over 100 meters square, and it would be 2 Pascal. And pressure on side Z is equal to, if you calculate it, 150. The values are just for understanding. Over 100 meters square, it is 15 Pascal. Now I have to discuss one important thing. The pressure on the side faces. For example, if we look for the side faces, let me draw the whole box and let's discuss the pressure on the side faces. For example, pressure on the side faces can be marked as, what you need to know is that we are discussing the side faces. Let me clear that if I call this side face as P, the front one as Q, the back one as R, and this is S. So these are the side faces. Q is the front face, R is the back face, P is on the right side, and S is the left side. If pressure on P is, for example, it was, as you see, 150 over 100, it was 1.5, I think. The values are just for understanding. 150 over 100, it was 1.5. Sorry, it was 1.5. The values were just for understanding. Now you see, pressure on P was 1.5 Pascal. Pressure on Q is 1.5 Pascal. Pressure on Z is, sorry, pressure on S, or you can say that R, is 1.5 Pascal. Pressure on S is 1.5 Pascal. Pressure on every side face is 1.5 Pascal. Now, what is the total pressure on the side faces? Total pressure on the side faces will remain 1.5 Pascal, as total force on all the four faces will become, it is 150 into 4, it will become 600 Newton. And at the same time, area of the given four faces will also become 100 meters square into 4, it is 400 meters square. Basically, when you increase the number of sides, the force and area will increase in same ratio and the pressure will not be affected. So even if you calculate total pressure on the side faces, will get same answer as 600 Newton will be the total force and the area total will be 400 meters square. So it will become 1.5 Pascal. Basically what is the concept here is that if you make calculation only for P, then the force is 150 and the area is 100 meters square. When you take P and Q, the force and area both become double. When you take P, Q and R, the force and area both become triple. When you take P, Q, R and S, the force and the area all become triple. So when you take pressure, you see it is not following the vector addition or scalar addition. Although we take it as a scalar, but yet if you see the concept, when you take more sides, the pressure will not increase or decrease. The reason being, when you take multiple sides or you increase area, increasing the area increases both the force and area. So when the force and area increase in same ratio, the pressure is not affected. Let me clear this in this way. For example, if this is a sheet kept in a liquid and this sheet has, let's suppose, 6 parts, 6 equal parts. Every part is 1 meter square. Now, if you increase the area of the sheet, the liquid in contact with the sheet will also increase. Now, if we name these parts of the sheet kept in liquid as A, B, C, D, E, and F. So as you increase the area of the sheet, the liquid in contact will also go on to increase. So the parts that we are taking, the area and what will be the force due to liquid and what would be the pressure. A sheet in a liquid. For example, if you take part A only, part B only, part C only, part D only, part E only, part F only, then the concept is that if you take any one single part, if the area is 1 meter square and the force is 100 Newton for A, this will repeat for B. This will repeat for C. This will repeat for, the values are just for understanding. This will repeat for D. This will repeat for E. This will repeat for F. Now, if you take A plus B, if you take A plus B, the area will become 2 meters square and the force will also become 200 Newton. If you take A plus B plus C plus D plus E plus F plus, that's it. Then they are, you see, they are in total 1, 2, 3, 4, 5, 6. The area will become 6 meters square and the force will be 600. In any case, when you calculate the pressure 100 over 1, it is 100. 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 Now, when you double the area, in a container of liquid, if you take some surface whose area becomes double, then the force will also become double, and as a result, the pressure will still remain 100 Pascal. Here, if the force becomes 6 times in the liquid, then the area is also becoming 6 times and still the pressure remains 100 Pascal. So the pressure is only depending on the depth and not on the area of the surface that you're taking. So the basic concept that I want to teach here is that the pressure in a liquid depends on the depth of the liquid and not on the area of the surface on which the pressure is exerted. Sorry, I'm making this lecture late night, so I'm a bit sleepy, so please excuse me. Now, if you use this concept to calculate the upthrust, first of all, if you have a container of liquid like this, and it is filled with liquid fully, and you immerse some object in it. For example, you have a cylinder here in this liquid, then the pressure is distributed in all the area of the cylinder that can be used to calculate the force. On the top surface, the pressure will be low as the depth of the liquid is very low. As you move downwards, the pressure will increase because of increase of the depth. While moving downwards, the pressure will increase because of increasing the depth. However, on the side surfaces, the pressure will go on to increase because of increase of the depth. Yet on the bottom, pressure will be further increased because of increase of the depth. So the total pressure on the top is, let's suppose, P1. Total pressure on the bottom is, let's suppose, P2. On the right side, it is P3. On the left side, it is P4. With respect to the given container, P3 and P4 is equal, yet it will not cancel out. So pressure is a scalar. Scalars do not cancel from opposite sides, although the pressure on the sides, that is a horizontal pressure, although the pressure P3 and P4 is equal, yet it will not cancel out as pressure is a scalar. As pressure is a scalar, so it will not cancel out. Yet it's a squeezing effect. The total pressure on the vertical sides, what are the vertical sides? This AB and this CD are the vertical sides. The total pressure on the vertical sides is either P3 or it is P4, yet it will not be added up or it will be subtracted, because if you double the sides, the area will become double and the force will also become double and the pressure will remain same. So we can call that P3 is equal to P4 is equal to P on vertical walls. This pressure cannot increase or decrease. You cannot add it or you cannot subtract it, because pressure is independent of the area of the walls and P3 and P4, which is acting on the vertical walls, and the pressure that is acting horizontally will be equal, and you can call it as P. So total pressure on the on the vertical walls is P3 or P4, and it will generate a squeezing effect. The cylinder or the box will be deformed or it will be squeezed because of the pressure acting on the vertical walls, and this pressure is acting horizontally. When we go for the forces on the vertical walls, there are two things which are important. Net force on vertical walls will be zero, as force is a vector, and if we take P4, a force towards right, say it is F4, then F3 will be P3 times A, and this will be towards left. F3 and F4 are equal and opposite. They will cancel out and the answer will be 0. So on the vertical walls, there is no net force. However, the total pressure, on the vertical walls, is either P3 or it is P4, and you can call it P as well. Because you cannot add it, you cannot subtract it, and what is the answer of an individual pressure? It will be the pressure on the four walls, because it cannot be added or subtracted. However, the net force on the vertical walls, force is a vector. Since force is same from all the sides, and when the vectors have a uniform distribution or they have equal values from opposite sides, they cancel out. Net force on vertical walls AB and CD will be 0 Newton, and the reason for this is because of cancellation. The net force on the vertical walls is 0 because of the cancellation. So the cancellation is the factor which makes the net force 0 on the vertical walls. Now let's go with the horizontal walls. For the horizontal faces, there are 4 vertical faces and there are 2 horizontal faces. On the vertical faces, the force is cancelled out, while the pressure remains. Pressure on all the 4 walls is same as pressure on any one of the walls. Now the horizontal faces. There are 2 horizontal faces, the top face and the bottom face. If we draw a 3D drawing, then this is the top face, and pressure on the top face is, let's suppose, P1, and area of the top face is A. Area of the bottom face is still A, and the pressure on the bottom face is P2. Now, if we calculate the net force on the horizontal faces, or we can call it net vertical force, then force on the top. We can subtract forces but not pressure. It's P1A. Force on the bottom is equal to P2A. P1A is acting downwards, P2A is acting upwards. And what is their comparison? P2 is obviously a bigger pressure. Because of depth, it is more. At more depth, you have more pressure. At less depth, you have less pressure. P2 is greater than P1 as it is acting. It here is P2 as it is acting at more depth. So the pressure that is acting at more depth will be greater, and the pressure that is acting at less depth will be less. Now you see, if we call F1 as, F1 is the force that is acting at the top as P1 into A, then F2 is a force that would be equal to P2 times A, and the net force, this force is downwards, this force is F upwards, and the forces, these two forces are not balanced because F2 is due to the pressure that is acting at the bottom face. So F2 is greater than F1, and the net force that you will get is, the net force that you will get is, it is F2 minus F1. Now if we substitute the values, the net force will be P2 times A, assuming that the area of the object is uniform. P2A is the force on the bottom, P1A is the force on the top, and if we take A common, the net force that is upwards will become P2 minus P1 times the area. Now, if we consider the whole picture, then we have to understand that if this is the liquid, then for this cylinder, P1 or F1 is acting at the top, P2 is acting at the bottom. Now, if we care about depths, then the depth of the top is, let's suppose, H1, and the depth of the bottom is, let's suppose, H2. And one important thing, the length of the object, this could be the total length or the length immersed for the object, is, let's suppose, L. L is the immersed length, and as you observe, H1 is the depth of the top, H2 is the depth of the bottom, and L is the immersed length of the object. Then you see, formula for P1 will be, P1 is equal to rho G H1. P2 is equal to rho G H2. Now, if we calculate the net force, then it would be net force is equal to the force at the bottom, P2A, minus the force at the top, that is P1 into A. Now, if we substitute the values to calculate this net force, which is upwards, and this net force is, this is called upthrust, then the upthrust can be given as, this upthrust, which is the net upward force, can be given as P2 is rho G H2 into A, minus P1 is rho G H1 into A. So rho G into A is common. Upthrust will become rho into G into A into H2 minus H1. And H2 minus H1 will become L. This is the immersed length. So finally, the formula that we'll get for upthrust is density of the liquid into G into A into the length of the container or the immersed length. So this is the final form of the formula for upthrust. So we can say that upthrust can be given as Upthrust can be given as density of the liquid into acceleration due to gravity into area into immersed length. Now, a more refined form of this formula could be, if you combine these two terms, then it would become area into immersed length could be written as immersed volume. Area into the immersed length, 1 second, multiple of area and length is, volume, but when you multiply area and immersed length, it becomes immersed volume. So new formula for this could be upthrust is equal to density of the liquid into acceleration due to gravity into volume of the object that is immersed in the liquid. So if we multiply density of the liquid, acceleration due to gravity, and the volume of the object immersed in the liquid, then this will give you the upthrust force that is acting upwards in the fluids or liquids. And one thing that you should know, upthrust is due to the pressure difference. This pressure difference exists in fluids which are gases and liquids, and this pressure difference, due to the pressure difference on top and bottom of an object. So upthrust is due to pressure difference on the top and the bottom of an object, and it is an upward force that tries to bring out the object from the liquid. And its formula is, it is multiple of density of liquid, acceleration due to gravity, and the volume of the object immersed in the liquid. In this slide, we'll cover up to this point. In the next slide, we'll see different factors affecting the upthrust and problem solving about upthrust.